All right, so today we're going to be looking at doing compound interest, but with the recurrence relationship rather than the regular compound interest formula that we're used to. So the regular formula that we are used to is this one here, and that's the interest equals the principal multiplied by 1 plus the interest rate that's altered by the compounding period to the power of the compounding periods that we would have over the years. Great formula to use, helps us project somewhere into the future. So if I wanted to know 100 years into the future, what would my interest look like? 30 years, something like that. The only problem is if I was to try and break this down into step-by-step progression, it's a much more complicated formula to use, especially if I was just wanting to do one after the other. So that's where we start to use a recurrence relationship. So our recurrence relationship is this one, and it just tells us that the original term multiplied by a common ratio gives us the next term. That next term becomes the original term. We multiply that by a common ratio, it gives us the term that's after that. And it just continues, and it helps us model the situation a lot easier. So that's what we're going to try and do. So our first example is compounding once per year. Easy example to start us off. All it's asking for is what is the common ratio by analyzing the problem. And I can see that we've got ourselves an interest rate, which is 7.5%. But unfortunately, that's not our common ratio. That's not the thing that I can multiply it by to increase it up. Otherwise, I'd be getting a lot of money every year. And unfortunately, the world just doesn't work like that. So what we're going to be doing instead is we're going to say, well, our R value, especially when we're looking at something where it's appreciating and it's going up, it's going to be 1 plus whatever that interest rate is as a decimal. So we're going to have to do that by changing 7.5% and reducing that down to its decimal by dividing by 100. And that will leave us with a common ratio of change for each year at 1.075. Now, it doesn't look like that's such a fantastic rate, but if this progresses on top of itself over and over and over again, and especially if you have a great starting principal, it's going to keep on increasing dramatically. And we call that exponentially as it builds on top of the one beforehand. Now, it's asking for a recurrence relationship, and that's Vn plus 1. Well, what we had up above was An plus 1, so I'm going to use An plus 1 instead. So we're going to say the next term, An plus 1. I've got the first term, or I've got what we would call the 0th term. So I'm really going to look for, well, what's the next one? I would, at the moment, since it's only asking for a modeling of n plus 1 years, I would keep it generic. I'm not going to write A1 and my initial one being A0. I'll use that later when we try and work through it. So I can start off as An plus 1, and that is going to be equal to R, which is 1.075, multiplied by my initial term. And my initial term for this is An. So generic, and I'm keeping it generic even though I know that we're going to insert $2,000 for the investment, but that's because maybe they'll change their mind at the last moment. Maybe they'll invest a little bit more, maybe a little bit less. Maybe I'm going to use this for somebody else. So there is our generic recurrence relationship, and you can alter that if you wanted to go 1.075 times 2,000 if you know that investment isn't going to change. So moving on down to the next one, we're going to use that recurrence relationship for the investments. So it's asking for the first year, second year, third year. So all I can do is I can use my generic one. Since I haven't got much space, I'm not going to rewrite the generic, but I normally would. And I can go down, well, I want to know what is the first years after the 0th year, which is how much I'm investing it at. And that would be this value here. I'm investing it at $2,000. So it's A1 equals 1.075, and we'll times that by my initial value, or my A0th term, and that would be the $2,000. So get a calculator out. If it's a nice easy sum, we don't need to, but I'm feeling lazy, so I'm going to go 1.075. That gives me $2,150. So after 1 year, my amount, and remember this is an amount now, this isn't like when we do the interest formula where it only gives us the interest, it gives us the new value. So the interest formula, if I was to have substituted in the values that I know, I would have gotten an answer of 150 because the interest that's increased from 2,000 to 2,150 is 2,150. Now, this is why compound interest is so great. If I'm looking for the second year, I'm going to do the same process, 1.075, but I'm going to multiply it by how much my money is worth at the first year, because I'm now using the recurrence relationship to get the next year after it. So my now value is 2,150. And if you already got that saved onto your calculator, you can hopefully just do answer times by 1.075. And from now on, you can just keep on writing, you can just keep pressing equals, and it will keep on multiplying that number by 1.075. So if you're wanting to try and get 10 years worth of data, you can do that nice and quickly once you've done the first two. But that comes out to be 2311.25 after the second year, or at the end of the second year. And it's asking for 3 years, so I'm going to just do that process. Again, A3 equals 1.075, which is that common ratio. And I'm going to multiply that by the exact same process, the second years, to get me the third years. And again, since I've got that answer saved, times that by 1.075, so we're not doing too much rounding. We can round on our answer. We've got 2484.59375. We're going to go to 2 decimal places since that's what most money should be going to. So 2484.59. 2484, not 8. 2484.59 approximately. I've got a bit of a jammy mouse today. So that's our first bit. Nice and easy. It takes us a little bit of time, especially when you're doing it on a computer, but if you're doing it by hand, I think that would be a lot easier. So it's saying, during which year will the investment first exceed 2,500? Now we can see in the first 3 years, it doesn't exceed it. But the way that this is exponentially increasing, I can already see going from here to here, there is an increase of more than $100, and we're only $15.41 away from exceeding 2,500. So I know from this particular answer that between third year and fourth year, the initial investment will exceed 2,500. However, since it compounds yearly, it won't exceed $2,500 until the fourth year, because we won't be able to get it out of the bank until it's actually gotten that interest, since we have to wait. Unless this is a special bank, or unless there is more compounding hiding behind the scenes that we don't know, it could increase to 2,500 after a couple of months. But seeing that we're going yearly, by the third year, not good enough. By the fourth year, we'll have plenty. It will have exceeded 2,500. All right, so let's step up the game a little bit. We're going to go into the second example where we're going to be saying, well, what happens if I am changing this not yearly, but compounding it instead at a different interval? So we can already see that they filled in some of the bits for us. So they're saying that we can already see that the rate that they've been giving us is 4.5%. And we know that we've got a K value, which is a compounding period, and it's saying that that is quarterly. So that's why there is a 4 next to the K, because there's 4 quarters in a year. So what we need to do is we need to break this down into a yearly thing. We're breaking it down from a yearly thing down to a compounding interest. So what we're going to do first is we're going to do the same process as before. We're going to get our rate that we would normally do. It's saying 1 plus, we would do our rate value, which is the 4.5. And we would normally divide that by 100. But if I only did that, that would give me a common ratio for a year. And we don't want it at a year. We want to break that down to compounding. So I'm also going to divide it by the 4. Since it's on the bottom, it's actually going to multiply with that 100. So we can do 4.5 divided by 400. And we can plus our 1 onto that to give us 1.01125. 1.01125. Now it's going to look like that's very disadvantaged because we're getting such a low rate now, but we're compounding much more frequently. So we'd find even though 4.5% at a yearly rate will look a lot nicer in terms of the common ratio that we have, the fact that we're doing it so many more times throughout the year will actually make sure that we end up with more money at the end. So it's asking for the recurrence relationship. So we're going to do the same thing as before. We're going to go AN plus 1 equals our common ratio of 1.01125. I'm not rounding just yet, just because it's going to have a big effect having a 0.011 versus a 0.01125. And that's going to be multiplied by our term that's before AN plus 1, which is just AN plus 1, meaning you've added 1 on top of AN. So now it's asking, use your recurrence relationship to determine the amount Brian owes after 3 quarters. So unfortunately, I didn't read the question. Brian's borrowing money. That means they're going to be earning some interest. The bank's going to be earning some interest. That's assuming that he's not paying back regular intervals. We haven't looked at anything about him repaying intervals. We're just saying he's put 5,000 in there. He's not paying it back yet. They're going to just keep on accruing interest. So 3 quarters. So we're going to have to do this process 3 times. So we're going to say, okay, well, we know A0 is 5,000. So A1 is going to be 1.01125 times by $5,000 that Brian borrows, which is going to give us, times by 5,000, give us $5,056.25. Now, since this is going to take a similar process as before, I'm going to skip a little bit of my working because it's going to take me a long time to do it on the computer. So my A second term will just be that value there multiplied by the common ratio. So I can multiply that by the 1.0125. Oop. Let's try that again. 0.1125. And I'll end up with 5,113.13 cents. So 5,113.13 cents. And following that process down to the 3rd quarter, because that's what we're interested in. Multiply that again by the 1.01125 to give us 5,170.66, because we're going to round that up. So 5,170.66. So just like that, after 3 quarters of the year, he's already going to need to owe another $170.66 on top of the 5,000 that he already invested, assuming that this place is going to compound it quarterly. But that's exactly the kicker. This company must have now decided we're not going to compound quarterly anymore. We're going to compound monthly instead. So now he's going to owe it back at a quicker rate. And what we're going to look at is after 2 months, how much money is he going to owe back? And we're hopefully going to see that it might not be the same as the 5,056.25, but it's going to get there quicker. It's going to get closer to it. So if it's going to be compounding monthly, well, we're going to have to do what we did up in A, but instead of doing the times by 4 at the bottom or divided by 4, we're going to be dividing by 12 instead. So we would have 1 plus, we're going to do 4.5 because it's the same interest rate because we have been told otherwise, 100 and 12 months of the year instead. Again, this is going to look like it's not going to hurt too much because it's going to look like a very small rate, but it's happening so much more often. So it's going to be a bit of a painful rate for Brian. So we've got 1.003, I think it's 75. And it's asking for that recurrence relationship, so we can just write it out as AN plus 1 equals our common ratio of 1.00375, which you can already see is smaller than the common ratio of the one above. But again, we're compounding it more frequently. So it's going to keep on stacking on top of itself more times in the year than what it would have in the quarterly, or what it would have definitely in just 1 year. So there we go. We've got our recurrence relationship, and we use that to get the 2 months. So I'm going to go A1 equals my common ratio of 1.00375 times it by how much he put in to begin with, which was $5,000. And we are going to end up with $5,018.75. So you can see nowhere near the amount that was above, but this is quarterly. That means after 4 months, and we're almost already there after just 1 month. The part where it starts jumping on top of itself, though, hasn't happened yet. So it does look like it is a quarter of that amount, because it is a quarter of that amount. It won't be after we multiply it by the common ratio again of 5,037. What do I have? 0.57. If I was to look at having 2 times that, or 2 times this amount, this interest rate here, we'd have 36 and we'd have 37.5. I know it doesn't look like it's that much more. We've only got a little bit extra cents, but if it just continues this way, it will pile up on top of itself because we are compounding more frequently. And that's all asked for after the 2 months, which leads us on to our final question. Now, our final question is not an increased rate anymore. We're looking at a decreased rate instead. So we're looking at something that's going to depreciate by a certain amount. And depreciate just means that it's decreasing by 7% in this case per annum. Luckily for us, this problem doesn't involve example 1 and example 2 combined. It's just an example 1 problem with just a depreciation, but you could have a depreciation at a compounding rate, and we would have to try and work with that. But our rate is 7%. So write that off to the side, 7%. But when we're wanting to try and work out a common ratio that we can use, we're going to have to do what we did before. Instead of doing the plus, we have to do a take instead though. So we're going to have 7% less than 1. So we would have 7. And again, we want this as a decimal. So we would do divided by 100. We're not compounding by a certain amount. We're going to assume it's compounding by year, especially if I look through the problems that go down a bit further, it asks for years. So that's all we're interested in. And we are going to say that that is 0.93, which makes our recurrence relationship AN plus 1 equals 93% of what it was originally, which is AN. Or AN has reduced by 7% to get us AN plus 1. So we can reuse this, we can use this recurrence relationship similar to what we had before, where we do A1 equals our common ratio multiplied by the amount. Again, I'm going to try and go through this a little bit quicker. The amount that they're getting at is $6,900. And that will work out our A2 value. So we can do that quickly. 6,900 times it by the 0.93 to get us 6,417. So their original value of 6,900 is now only worth 6,417, the year after. And we can do the same process for A2. We use the common ratio and multiply by the first year's one, so this 6,417, to end up with 5,967.81. So has it dropped? This one going from here to here has dropped by about 400. This one going from here to here, again, dropped by a bit more than what it did originally, but about still 400 and something. We can work out the third year after that. It's asking for the nearest cent, which I wasn't looking at before. So look, 0.81, I think that's good enough. That's our nearest cent. Unless it's asking for 10th cent, but it hasn't asked for that. So I'm gonna go 5967.81, multiply that by our depreciation of 7%, which is 0.93, and we'll end up with 5,550.06, and that's me rounding to my nearest cent. And we can see that this thing is dropped by 400 and something again. And it's going to keep on going like that, dropping down, dropping down, dropping down. But we can see that it's dropped down by less than what it did before. And the reason why it's doing that is because we're taking a percentage of something that's not worth as much now. And so the dropping that it's going to be having is going to be less effective. Now it's asking, what was the depreciation during the third year? Now we can take this two ways. The way that we can take this is how much has it depreciated from the second to the third year, but it's asking during the third year. So I'm going to assume it's going from A3 to A4. So I'm going to work out the A4 value by doing the exact same approach. We do that 5,550.06, and we would times that by our 0.93, which is the 7% depreciation. We would end up with 5,161. And let's round it off a little bit. We're going to have 5,6, giving us our new amount, not the amount that it's depreciated by. It has gone from 5,550.06 down to 5,161.56. So our depreciation is the difference between those two values. So we can do A3 minus A4 will give us the difference between those two values. Now, that's going to give us a positive value that it's depreciated down by. If you were to do this normally, I would recommend to go A4, take away the third term, and it will give you a negative value, which I was going to try and avoid, but I think it might be a little bit more beneficial for us to do, because we're going to end up with a negative value, and that is because we're taking a bigger number from a smaller number, but it demonstrates that depreciation. How much has it dropped down by? How much has it gone down by? So we can do that minus the 5,550.06 to get 388.5. So 388.5. And since this was approached as a worded question, I would answer it as a worded answer, and I would say it has depreciated, and we can put our dollar sign in, it has depreciated by $388.5. It has reduced by $388.5. All right, hopefully this was helpful for you. If you have any more problems, try and contact one of your teachers. Make your way through the independent work here on the OneNote. I would recommend answering, putting some spaces in yourself, or working off to the right. Or do it in your book if that's a lot easier for you, and just take a picture of it and scan it up to the OneNote so that we can monitor your progress. All right, thanks for watching.